3. Statistical applications in environmental sciences. Module 16 Concepts of population, sample and confidence interval. 1. Introduction. Concepts of population and sample are ubiquitous in any statistical analysis. A thorough distinction between them is essential for a comprehensive understanding of the underlying concepts. In this module, concepts of samples and populations are thoroughly expounded. Theory of confidence intervals is introduced and how C connects sample to population via student's t-distribution. We will also learn how to compute 95% C for a number of statistical measures, including sample mean via parametric and non-parametric approaches, standard deviation, binomial distributions, proportions, and Poisson distributions count data. 2. Learning outcome. A. To learn concepts of population. B. To learn theory of confidence intervals. C. To learn calculation of 95% confidence intervals for mean, SD, Poisson and binomial data, D. To learn calculation of C of mean through resampling bootstrapping approach. 3. Population and sample. The term population is used to refer different meanings in different contexts. For example, consider birth weights of newborns in a particular city over a year period. There were 10,000 childbirths in that particular city. Here the population consists of all those 10,000 newborns. Instead of measuring the weights of all those newborns, which is not challenging in this case, let's decide to measure birth weights of only 50 random newborns. This subset is what is known in statistics as sample. We can use sample as a proxy for entire population and extrapolate measurements done in sample to make conclusions about the populations. In biomedical research, population is not only a much larger dataset consisting of target people, for example, males in India, but also the future generations, therefore we assume that it is infinite. In experimental research, population means the ideal situation or underlying mechanism. For example, Gregor Mendel studied 929 pea plants in F2 generation, his sample to arrive in generalized 3:1 phenotypic ratio dominant, recessive in ideal population. His phenotypic ratio of 3:1 is a model, a mathematical description of a simplified view of nature. He used his samples to extrapolate an underlying phenomenon, his model, that is applicable to diploid organisms in general. Statistics goes from sampled specific things to population general conclusion and model, and therefore it is considered as an example of logical induction. On the other hand, probability is an example of logical deduction as it goes other way around, from general to specific. 4. Statistical applications in environmental sciences. 4. Population versus sample notations. In general, abbreviations notations of statistical parameters are presented in Greek alphabets for populations and Latin for sample. Population Greek, sample Latin. Mean micromean x variance sigma 2 variance s2 standard deviation sigma standard deviation s median nu median x. Proportion pi proportion p. 5. Theory of confidence intervals. Let's consider our former example. We precisely know the birth weights of 10,000 newborns in a particular city over a year, and let's consider it as our population. We have also calculated mean birth weight, 2.7 kilograms population mean. Out of 10,000 newborns, we have randomly selected 50 newborns, our sample, and calculated the sample mean. The value of sample mean could be more or less than the actual population mean. Let sample mean be 2.6 kilograms with 0.1 kilograms as standard deviation. We will first calculate a statistic called t-ratio from this, t equals m micro s square root n. Where m is sample mean, micro is population mean, and denominator s square root n is sample SEM. T-ratio can be defined as difference between sample mean and population mean upon sample standard error or the mean. T equals 2.6 minus 2.7, 0.1, square root 50. Equals minus 0.1, 0.141. Equals minus 0.70922. The value of t-ratio is a bit less than 0. This is expected, as the sample mean will be more or less close to population mean, numerator of t-ratio will be close to 0, so the ratio will hover around 0. Now we take yet another 50 random samples from the same population and calculate t-ratio. We repeat this 100 times and plot the distribution of t-ratio, like how we plot a histogram. The distribution would look like this. 5. Statistical applications in environmental sciences. This is one way to convert approximate Gaussian distribution to a symmetric distribution, but for this method, you should know the true population mean. True population mean remains unknown mostly, except in this kind of simulation studies. As explained, t-ratio will be centered around 0, peak at 0, because most of the sample means would be close to population mean. The shape of t-distribution depends upon degree of freedom, df, which is equal to n1. If the area under 2.5% of total area at both the tails, i.e., most unusual t-ratios whether it is too low or too high, is chopped off, the resulting area would include range of t-ratios that include 95% of samples. To get 95% area, we have to chop the tail precisely at a t-score at both the directions. This t-score is called t or t-critical. In this case, with degree of freedom 49 and significance level 0.05, because we have to chop of 5% of most unusual values, t is 2.01 calculated using online calculator as explained below. That would mean, if we cut the graph at minus 2.01 and plus 2.01, shaded area in figure, we will get range of t-ratios that include 95% of samples. The shape of t-distribution, so as t depends upon degree of freedom. For a particular significance level, we can calculate t from t-distribution table, or using an online calculator. As stated earlier, t-ratio equals m micro s square root n. We can rearrange this equation. To solve for micro, the true population mean. For the sake of brevity, derivation of following formula is omitted. Micro equals m plus or minus t s square root n. Where m is sample mean, t is constant from t-distribution, and s square root n is sample SEM. 6. Statistical applications in environmental sciences. Given the sample mean m, sample standard deviation s and sample size n, it is possible for us to define ranges that include the real population mean with confidence. As already explained, t depends on the desired confidence, which is arbitrarily 95%. If t for 95% confidence is used, the resulting ranges of sample means would include the true population mean 95% of times. This range is called 95% confidence interval. 6. Confidence limits, levels and intervals. The desired amount of statistical confidence is called confidence level. For e.g., if you want a very high confidence on your results, you should choose 99% confidence level as part of your experimental design. Confidence level is chosen before experiment is conducted and it is not ethical to change the CL after the data is generated. If you had chosen 99% CL, you will generate 99% confidence interval after the experiment. Confidence interval is a range lower limit to upper limit that plot the precision of your sample measurement in comparison with the true population value. Two values that limit this range, the lower limit and upper limit, are called confidence limits. 7. Confidence interval of mean. Confidence interval of the mean tells you how precisely you have determined the sample mean as an estimate of population mean. On the other hand, precision depends on confidence level, CL. CL of 99 is more precise estimate than 95, which is better than 90. As precision increases, wider would be confidence interval. For example, 99% C is a lot wider than 90% C. Another statistic standard error of the mean is also similar to C. SEM also tells you how precisely you have determined sample mean comparing with population mean. However, confidence level of SEM is very low, only around 60%, so SEM is quite an inaccurate measure to quantify precision. 95% C is routinely used across biological and environmental sciences. In situations where whole population is used to calculate statistic, for example mean of population, confidence interval makes no sense. Consider a class with total strength 24 students and mean mark 11.8 out of 25. Here 11.8 is the population mean and we are 100% sure confident that the true population mean is this value, no question about it. However, out of 24 students, if I randomly select 8 students and calculate their mean marks, that mean would be sample mean and C makes sense in such situations. 95% C of sample mean can be calculated using two methods. The parametric distribution dependent method assumes that our sample is sampled from a roughly Gaussian distribution. This method utilizes a constant from t. 7. Statistical applications in environmental sciences. Distribution t for calculating 95% C of sample mean. We have already explained how this formula is derived in earlier section. Formula is m plus or minus t s square root n. Where m is sample mean, t is a constant from t distribution, s is sample standard deviation and n is sample size. Also note that s square root n equals SEM, standard error of the mean. We can calculate 95% C of sample mean given sample mean, sample standard deviation and sample size. Raw data is not necessary. Confidence interval is a numerical presented as sample mean plus or minus C, written as lower limit to upper limit, e.g. If 95% C is 6 and micro equals 51, C range equals 45 to 57. Notation like 51 plus or minus 6, which is commonly used to describe standard deviation, is not used to describe confidence intervals. Let us consider an example for calculating 95% C of sample mean. Test marks data with mean equals 12.81, S equals 4.905, N equals 24. As N equals 24, DF is 23. Let's first look up T for 95% confidence level with DF equals 23. T is 2.0687. Let's now calculate W. The width of 95% CW equals T S square root N. Equals 2.0687 asterisk 4.905 square root 24. Equals 2.0687 asterisk 4.905 4.90. 8. Statistical applications in environmental sciences. 9. Statistical applications in environmental sciences. Equals 2.0687 asterisk 1. Equals 2.0687. Finally, 95% C of mean is mean 2.0687 to mean plus 2.0687 10.7413 to 14.8787. In case no standard deviation or mean are given but presented with raw data, we have to calculate mean and SD to calculate 95% C. Microsoft Excel formula for T and C formula is equals TINB alpha, N1. Where alpha is level of significance, 0.05 to calculate 95% C. An online calculator for calculating C of mean is at 10. Statistical applications in environmental sciences. Nine. Statistical applications in environmental sciences. 10. Statistical applications in environmental sciences. For calculating C of mean, there are a number of assumptions. A major assumption which is often overlooked is that the sample must come from a population that is Gaussian or roughly Gaussian. If the distribution is log normal etc., C cannot be calculated using the above method. Samples have to be random. If samples are deliberately chosen non-random, C cannot be calculated. This also applies if some cells in suspension are clumped, therefore not homogeneous. Patients from a particular clinic too are heterogeneous. Instead of random samples, situations where true randomization is impossible, we use convenience sample, as in the case of patients from a particular clinic. An alternative approach for calculating C of mean is nonparametric, rank-based, and therefore, do not make explicit assumptions about probability distributions. For example, out of our 24 students, we randomly choose 5 students and their test marks are 22, 14, 11, 2, 9. Step 1. Rank order these values. Rank values 1, 2, 2, 9, 3, 1, 1, 4, 1, 4, 5, 2, 2. Step 2. Make a new subset by picking 5 random integers from 1 to 5, and picking the value with that rank. Repeat is allowed. For example, you mark 5 pieces of papers with 1 through 5 and place it in a box, as in a lottery. Shuffle the box and randomly pick a paper, record its value, and put the paper back to the box. Shuffle, pick once again, and so on. You might get same numbers multiple times, and that is allowed. For example, suppose you got 1, 3, 3, 4, 5. Now you should record values of those ranks to make a subset 2, 11, 11, 14, 22. This new subset is called pseudosample. Do this many times. Pseudoreplicates, say 500 pseudoreplicates to generate 500 pseudosamples. For each pseudosample, calculate mean. Next, rank order those means. Total 500 values from minimum to maximum, and pick 2, 5th and 97, 5th percentile. As 97.52.5 equals 95, this range is the 95% C of mean. 11. Statistical applications in environmental sciences. This method is variously known as resampling method, bootstrapping, or computer-intensive method, and is extensively used in phylogenetics and genomics. A number of studies have revealed that this method is far superior to the early Ten. Statistical Step 2. Make a new subset by picking 5 random integers from 1 to 5, and picking the value with that rank. Repeat is allowed. For example, you mark 5 pieces of papers with 1 through 5 and place it in a box, as in a lottery. Shuffle the box and randomly pick a paper, record its value, and put the paper back to the box. Shuffle, pick once again, and so on. You might get same numbers multiple times, and that is allowed. For example, suppose you got 1, 3, 3, 4, 5. Now you should record values of those ranks to make a subset 2, 11, 11, 14, 22. This new subset is called pseudosample. Do this many times. Pseudoreplicates, say 500 pseudoreplicates to generate 500 pseudosamples. For each pseudosample, calculate mean. Next, rank order those means. Total 500 values from minimum to maximum, and pick 2, 5th and 97, 5th percentile. As 97.52.5 equals 95, this range is the 95% C of mean. 11. Statistical applications in environmental sciences. This method is variously known as resampling method, bootstrapping, or computer-intensive method, and is extensively used in phylogenetics and genomics. A number of studies have revealed that this method is far superior to the earlier method that uses a constant from t-distribution. However, this method is not suitable in case you would like to solve the question manually in a test paper. 8. Confidence interval of standard deviation. Standard deviation is an interval estimate. But how precise is your estimation of sample SD that plots scatter or variability of data in comparison with the population? 95% C of SD can be calculated using online calculators, for example. Input values are standard deviation and the sample size. For example, for our earlier marks data, 90 For example, for our earlier marks data, 95% C turns out to be 3.81 to 6.88. 12. Statistical applications in environmental sciences. As this C is an interval estimate calculated for another interval estimate that is SD, each original limit of SD will now be expressed as ranges. For example, upper limit of SD 12.81 plus 4.905 would now become a range between 12.81 plus 3.81 to 12.81 plus 6.99. Similarly, lower limit of SD 12.81 minus 4.905 would become 12.81 minus 6.99 to 12.81 minus 3.81. Microsoft Excel formulas for this are: lower limit equals DSQRT N1 CHIINB alpha 2 N1 upper limit equals SDSQRT N1 CHIINB 1 alpha 2 N1. For e.g., SD for marks data equals 4.67, N equals 34. Experiments with 2 possible outcomes, like gender of child, male or female, coin toss, heads or tails, etc., follow binomial distribution. Binomial distribution are commonly used in biology and are oftentimes expressed in proportions. Some examples are: proportion of monoecious plants in a quadrat. Proportion of an allele or a genotype in a population. One can calculate 95% of a proportion from value of numerator X or S, no, of successes and denominator N, total number of trials alone. For example, 45 out of 100 people were females. Here x is 45 and n is 100. Sample proportion, xn is 45 100 equals 0.45. To calculate 95% C of this proportion, head to an input numerator and denominator there. The calculator will return the values as 0.35 to 0.55. This means that there is 95% chance that the true population proportion of females that remains unknown to us falls somewhere between 0.35 to 0.55. That also means that there is a 5% chance that the true population proportion is either less than 0.35 or greater than 0.55. A method for manually calculating 95% C of a proportion is modified Wald method. 13. Statistical applications in environmental sciences. For example, in our earlier example P, called P prime, is 45 plus 2, 100 plus 4 equals 0.45. The width of 95% C equals 1.96x square root 0.45, 1 minus 0.45, 104. Equals 1.96x. 95% C equals 0. Another example, out of 10 diploid plants studied, 1 plant had A genotype, and the rest had A genotype. Calculate the frequency of A allele with 95% C. Here x numerator is 1 and n denominator is 20. Denominator is 20 because as plants are diploid, 10 plants together produce 20 sets of alleles. One can write down all alleles of these 10 plants to make the problem easy to understand. 14. Statistical applications in environmental sciences. As one can see, out of 20 alphabets, 19 are capital A, while only 1 is small a. So the proportion of A allele is 1 out of 20, or 0.05. One can either input these two numbers 1 and 20 in online calculator or in modified Wald method as explained earlier to calculate 95% C of the sample proportion 0.05. 95% C of proportion are 0.0013 to 0.2487. 11. Confidence interval of Poisson distribution count data. Count data like the mortality in an island, no. Of persons dead in unit time, number. Of bullets shot, no. Of mutations in a stretch of DNA molecule, or no. Of raisins in a laddu follows Poisson distribution if the measurements are random. From the count, C, alone, we can calculate the 95% confidence interval of the count. A good approximation for 95% C is more than 25 is C 1.96 square root C to C plus 1.96 square root C. For example, after dissecting 10 laddus, you found 25 raisins. Mean number of raisins per laddu is 2.5, but hold on, we will come to it later. First let's calculate 95% C of this actual count. C equals 25. Width of 95% C equals 1.96 square root C. Equals 1. This means that there is 95% chance that the real population mean raisins per laddu, which remains unknown to us, falls somewhere between 1.52 to 3.48. Mean raisins per laddu of our sample is 2.5, which doesn't say anything about how accurate the measurement is, or how approximate the measured sample mean comparing with the population mean. Remember that the formula given above is only an approximation if C is more than 25. An accurate calculator is available online at. Another example, there were a total of 10,000 deaths in an island over a period of 100 days. 15. Statistical applications in environmental sciences. This is because C depends on sample size. 12. Common mistakes. 1. For calculating 95% of proportion binomial distribution, it is important that no normalization is done prior to the calculation. For example, never express the measurement in percentage and calculate 95% C with 100 as denominator. Instead, we should use our empirical data. This is because C depends on sample size denominator, and that would not be 100 in most cases. For example, 2 out of 18 giraffes observed shows albinism. That means 2 are white giraffes and the rest 16 are normal. Here X is 2 and N is 18. You should calculate 95% C for 2/18 with sample size equals 18, not 11.11, 100. Sample size would then be 100, which would result in narrower C width. 2. For calculating 95% of count data, it is important to use total count value, not mean value. For example, in our earlier problem, don't take the average raisins per laddu 2.5 as C. In that case, C would be 0.62. 16. Statistical applications in environmental sciences. 7.2. A wider width. You should take C as 25 the total and calculate the C 16.1 to 36.9. Finally, divide both the limits with number of observations 10 to get C per event 1.6 to 3.6, which is narrower than had we used 2.5 as C. As the sample size increases, the width of 95% C gets narrower. 13. Summary. A. Sample is a subset of population and in most cases properties of population remains unknown. And we use samples as proxy to make inferences about the population. B. 95% C informs us how precisely we have calculated the respective sample statistic with respect to the true population mean. It is related to SEM. SEM is approximately 60% C, and 95% C is approximately twice the SEM. It is different from SD, as SD captures only the scatter of dataset. C. 95% confidence interval of mean can be calculated by using the formula micro equals m plus or minus t s square root n d. It is possible to calculate 95% C of mean without making any assumptions about the distribution of populations from which the samples came. The approach is through resampling bootstrapping. Manual calculation is almost impossible, but can easily be done in a computer. 95% C of standard deviation can be calculated in MS Excel or using a web-based calculator. Easily, though manual calculation is challenging. 95% C of Poisson distribution count data can be calculated using the equation C 1.96 square root C2. C plus 1.96 square root CG. 95% C of binomial distribution can be calculated using modified Wald's equation, or easily using a web-based calculator. 3. Statistical applications in environmental sciences. Module 17. Statistical hypothesis testing and p-values. 1. Introduction. Statistical hypothesis testing is the current gold standard of scientific methodology and is a key concept in inferential statistics. This involves defining two contrasting hypotheses, calculating p-value from the sample data and deciding the fate of the two hypotheses based on the p-value and the threshold cutoff significance level. Most common forms of errors in hypothesis testing are type 1 and type 2 errors. These errors can be minimized with appropriate choice of significance level. Most statisticians agree that p-value-based significance testing is overrated, and a simpler representation of 95% C is a better approach in most of the cases. A number of ways p-values can be decreased. The so-called p-hacking is common across scientific disciplines and it construes a scientific misconduct. 2. Learning outcome. A. To learn concepts statistical hypothesis testing. B. To learn significance levels and choosing the right significance level. C. To learn about type 1, type 2 and type 3 errors. D. To learn about p-values and discern a number of p-value fallacies. E. To learn about statistical power and false discovery rate. F. To learn the relationship between confidence intervals and p-value. 3. Statistical hypothesis testing. Scientific methodology was developed with Francis Bacon's Novum Organum, published in 1620. Subsequently, Karl Popper introduced concept of falsifiability that the scientific claims have to be independently verifiable, and Thomas Kuhn introduced concept of paradigm shift that the science progresses through unconventional revolution of ideas. How do we distinguish science from pseudoscience? The current gold standard for experimental scientific disciplines is statistical hypothesis testing, which is very intuitive to comprehend with a simple analogy. Let us design a very simple experiment that tests how lucky you are at any particular moment by coin toss. Effectively, by doing this coin toss experiment, you are testing two contrasting hypotheses. 1. You. 4. Statistical applications in environmental sciences. Are not lucky, and 2. You are lucky. There will be 10 toss trials, and even before the first coin is flipped, you decide that if you get 6 heads or more, you are deemed lucky. After flipping the coin for 10 times, you got 6 heads and 4 tails. Conclusion. Hypothesis number 1 that you are not lucky is rejected. Beware of double negatives. And conclude that you are lucky. Suppose you got only 5 heads, then your conclusion would be you fail to reject hypothesis 1 that you are not lucky, a triple negative logic jargon to say that you are not lucky. If you get 5 heads, instead of concluding you are not lucky, you take a correction pen and change your original design statement from 6 heads or more to 5 heads or more and conclude that you are lucky. Of course, this is not fair. This is cheating, and this form of misconduct is very common in scientific research. Another option is, instead of concluding you are lucky with 5 heads in 10 toss trials, you increase no. Of trials, you go ahead tossing coin 11 th time, 12th and so on till you get 6 heads on 13 th time, and suddenly stop the experiment there to conclude that you are lucky. Again, you take a correction pen and change the original proposition from there will be 10 toss trials to there will be 13 toss trials. Of course, this is cheating too. What is so special about 6 heads? Nothing, really. It is our threshold value for crisply deciding success from failure. Statistical hypothesis testing follows the following 4 steps sequentially. 1. Define alpha threshold p-value. 2. Define null hypothesis H0. 3. Define alternative hypothesis HA. 4. Calculate p-value, and decide the fate of hypotheses. First step is defining the threshold alpha. This threshold is exactly like the threshold of 6 heads we used in our example. 6 heads out of 10 trials constitute 60% confidence, so if you get 6 heads or more, you have 60% confidence to say you are lucky. However, experimental scientists want a lot more confidence in their conclusion to be independently verifiable. Karl Popper's falsifiability. Typically, they choose a confidence level of 95% or 9.5 out of 10. This would mean 5% tolerance of making incorrect mistakes. The tolerance for making incorrect mistakes is what is called threshold p-value or alpha. P and p-value stand for probability, and it is always expressed as a number between 0 and 1. A 5% tolerance for error expressed percentage is 0.05 tolerance level expressed in probability or p-value. In practice, the threshold value called alpha is almost always set to 0.05, an arbitrary value that has been widely. 5. Statistical applications in environmental sciences. Adopted. Ideally, you should set this value based on the relative consequences of falsely finding a difference false positive or missing a true difference false negative. More on this to be followed. Null hypothesis is usually the opposite of what you are trying to prove. In our first example, if you were trying to test the proposition that you are lucky, null hypothesis is that you are not lucky. If you are testing the efficacy of a drug, null hypothesis is that the drug is ineffective. If you are comparing means of two groups, null hypothesis is that their group means are equal. For clinical testing, null hypothesis is that the result is negative. For spam detection in email, null is that email is not spam. Alternative hypothesis is the hypothesis what you are usually trying to prove. In our earlier examples, alternate hypotheses is that you are lucky, or drug is effective, or group means are not equal, or clinical test result is positive, or email is spam. After completing your experiment and after performing appropriate statistical tests, you get a p-value. It is important to note that p-values and statistical tests only assess the validity of our null hypothesis defined in step 2 above. They do not test the validity of our alternate hypothesis directly. Therefore, we can make conclusions only about the null hypothesis. If you get a p-value, for example, 0.04, which is less than our predefined level of tolerance for errors, 0.05 defined in step 1, you may conclude to reject the null hypothesis and state that the results are statistically significant. If your obtained p-value, for example, 0.06, is higher than significance level alpha, then the conclusion would be not to reject the null hypothesis and that the results are not statistically significant. Remember that statistically significant does not mean scientifically or clinically significant. You cannot conclude that the null hypothesis is true. All you can do is conclude that you don't have sufficient evidence to reject the null hypothesis. This sort of arguments are called arguments by contradiction, often used in logic and philosophy. In our earlier examples, alternate hypotheses is that you are lucky, or drug is effective, or group means are not equal, or clinical test result is positive, or email is spam. After completing your experiment and after performing appropriate statistical tests, you get a p-value. It is important to note that p-values and statistical tests only assess the validity of our null hypothesis defined in step 2 above. They do not test the validity of our alternate hypothesis directly. Therefore, we can make conclusions only about the null hypothesis. If you get a p-value, for example, 0.04, which is less than our predefined level of tolerance for errors, 0.05 defined in step 1, you may conclude to reject the null hypothesis and state that the results are statistically significant. If your obtained p-value, for example, 0.06, is higher than significance level alpha, then the conclusion would be not to reject the null hypothesis and that the results are not statistically significant. Remember that statistically significant does not mean scientifically or clinically significant. You cannot conclude that the null hypothesis is true. All you can do is conclude that you don't have sufficient evidence to reject the null hypothesis. This sort of arguments are called arguments by contradiction, often used in logic and philosophy. An intuitive analogy is the similar situation in jurisdiction. Here H0 is accused as innocent and Ha is accused as criminal. A judge can pronounce the verdict is guilty, reject the null hypothesis, or not guilty, do not reject the null hypothesis. She can never pronounce that the accused is criminal, accept the alternative hypothesis, or innocent, accept the null hypothesis. Also, the juror's conclusion is crisp and clear, guilty or not guilty. She cannot say that the accused is probably guilty, or I don't know, as no one likes uncertainty in judgments. Similarly, in statistical hypothesis testing conclusion. 6. Statistical applications in environmental sciences. Is crisp and clear as it is based on the threshold significance level. A test that returns p-value of 0.4999 should be deemed significant while p-value of 0.5001 is not significant. Many statisticians criticize making this sort of crisp conclusions based on threshold p-value and overly emphasizing the term significant in papers. Many investigators do not report the exact p-value, like p equals 0.499, which is in fact very much borderline, and instead make ambiguous statements like, results are significant p less than 0.05. 5. Type 1 and 2 errors. As already stated, a significance level of 0.05 means 95% confidence level and tolerance of 5% error level. Even though this 5% level is very less, 5% of all results will be erroneous. Out of 100 statistical tests, 5 tests would lead to erroneous conclusion that the result is significant, while in reality the result would not be significant. For example, when you compare means of two groups, you got a p-value less than 0.05, therefore reject the null hypothesis and conclude that two means are significantly different, but in reality means are not different. Null hypothesis of no difference in means is wrongly rejected. Another example is that you go for an ELISA blood test to see whether the test is positive or negative. The test report says positive. The null hypothesis that you have no HIV infection is rejected, but this result is erroneous. You will never know is it an error or not unless you repeat the test many times or you already know the reality, for example, in simulations. This type of errors where null hypothesis is wrongly rejected, incorrectly rejecting the null hypothesis, is called type 1 error. We can also have yet another kind of error. The test report there is no difference in two group means, but in reality there is difference. A person is really HIV positive, but the test says he is HIV negative, false negative. A person is really guilty, but the juror pronounces the verdict is not guilty. The email is truly spam, but the spam filter says email is not spam. This type of error is called type 2 error or false negative, which is incorrectly not rejecting the null hypothesis. You've made a type 2 error when you wrongly do not reject null hypothesis. There really is a difference, association, correlation overall, but random sampling caused your data to not show a statistically significant difference. So your conclusion that the two groups are not really different is incorrect. 7. Statistical applications in environmental sciences. Decision. Reject null hypothesis. Decision. Do not reject null hypothesis. Reality. Null hypothesis is true. Type 1 error, false positive A. No error B. Reality. Null hypothesis is false. No error C. Type 2 error, false negative D. It is important to note that we will never know is it error or no error when we analyze the sample, unless the analysis is simulation in which the true population values in reality is known precisely, which is almost impossible when analyzing the scientific experimental data. There is yet another type of errors, type 3 or type S. This would happen when direction of effect goes opposite the direction of prediction, especially prone if you use one-tail p-values to be explained soon. An example of such an error happened in cardiac arrhythmia suppression trial CAST. Antiarrhythmia drugs like atenolol to control atrial and ventricular fibrillations were previously thought to either prolong the life of the patients or no effect, so the investigators chose to report one-tail p-value. They got a high one-tail p-value, so concluded the drug has no effect on prolonging the life. Actually, patients given drugs were 4 times more likely to die than placebo, so the effect went in opposite direction. 6. Choosing the level of significance. In the table above, quadrat denoted as A signifies false positives. Sum of quadrats A and B is the total of first row, null hypothesis is true. A plus B is alpha, level of significance. It is fraction of false positives when null hypothesis is true. If the null hypothesis is true, what is the probability of incorrectly rejecting it? That probability is the significance level. As already explained, a significance level alpha of 0.05 95% confidence is chosen almost universally in experimental scientific disciplines, especially in biological and environmental sciences. This traditional significance level is sometimes called 2 sigma level, as 95% of all values are expected within 2 standard deviations from the sample mean in normal distributions, central limit theorem of statistics. 8. Statistical applications in environmental sciences. Ideally, this level should be decided based upon the consequence of 2 main kinds of errors, type 1 and type 2 errors explained earlier. Use low alpha like 0.01 to have less chance of making type 1 error false positive, but beware, chance of making type 2 error false negative is increased. The consequence of setting alpha equals 0.01 would be more type 2 errors false negatives. Examples of type 2 errors include more spam in inbox, a criminal is set free, the test says negative for high plus person, a doped athlete is set free, and an effective drug is declared as ineffective and abort drug development. If these sort of false negatives are tolerable, choosing low alpha is justified. Use low alpha like 0.01 to minimize false positives and is ideal for situations when false negatives are tolerated like criminal jurisdiction. It is better to let many guilty person go free than to falsely convict one innocent person. Spam filter. It is better to have spam emails in inbox rather than automatically detecting as spam and deleting that. Article acceptance, or job selection, email, and clinical trial for Me Too, drug. It is better to abort an effective drug development than marketing an ineffective. Useless drug when better alternatives are already available. Use high alpha like 0.1 to have less chance of making type 2 error false negative, but beware, chance of making type 1 error false positive is increased. The consequence of setting alpha equals 0.1 would be more type 1 errors false positives. Examples of type 1 errors include good email declared as spam and deleted, an innocent is punished, the test says positive for high person, an innocent athlete is declared as doped and banned for life, and an ineffective drug is declared as effective and market it. Use high alpha like 0.1 to minimize false negatives and is ideal for situations when false positives are tolerated like civil jurisdiction. It is better to punish many innocent than let one huge illegal corporation go free, and clinical trial for novel drug. It is better to market an ineffective, useless drug than aborting the development of an effective drug when no drugs are available in the market. Please be noted that traditional 2 sigma level of 0.05 is not universally followed in other disciplines, especially in particle physics. To conclude evidence of detecting a previously known particle, accepted level of significance is 3 sigma alpha equals 0.003. To conclude evidence of the discovery of a new kind of particle, like in the paper describing the discovery of Higgs boson, accepted level of significance is 5 sigma alpha equals 0.0000003. 9. Statistical applications in environmental sciences. 7. P-values, correct interpretations and fallacies. Definition of p-value starts with the proposition, if the null hypothesis is true. The definition is, if the null hypothesis is true, what is the probability that random sampling would lead to difference as large as or larger than that observed in this study? Let us consider an example. A study compared mean of 2 groups, and got a p-value of 0.03. That means if 2 population means are identical, i.e., if the null hypothesis is true, there is a 3% chance of observing a difference as large as or larger than what you observed. As that chance is very low, 9 only 3 out of 100, you conclude that the means are not identical. Alternatively, you can conclude that random sampling from identical populations would lead to a difference smaller than you observed in 97% of experiments, and larger than you observed in 3% of experiments. P-value answers the question. In an experiment of this size, if the populations really have the same mean, what is the probability of observing at least as large a difference between sample means as was, in fact, observed? P-values are indeed confusing to many scientists because null hypothesis is almost always false. Logic works backwards population to sample, logical deduction akin to probability, and is counterintuitive. The hypothesis testing works on the principle of argument by contradiction. There are 2 types of p-values, 2-tail and 1-tail. A 2-tail p-value indicates critical region extends to both extremes of distribution, significantly large or significantly small. A 1-tail p-value extend only to either of the 2 tails of distribution. A difference between 2 can easily be spotted by looking at your null hypothesis. If the null hypothesis contains the symbol equals explicitly or indirectly, like, there are no differences between means, is equivalent to mean of group X equals mean of group Y, p-value should be 2-tail. If the null hypothesis contain the symbol greater than or less than explicitly or indirectly, like, there is no fever, is equivalent to temperature is less than or equal to 37 degrees Celsius, or, there is no profit, is equivalent to net gain greater than net loss, p-value should be 1-tail. A 1-tail p-value explicitly make predictions of the directionality of effect as part of the experimental design. This predicted directionality might very well be wrong too, that lead to type 3 errors explained earlier. When in doubt, always stick with 2-tail p-values. 1-tail p-values are always less than 2-tail p-values, so investigators like 1-tail p to prove their hypothesis. Some reviewers criticize any use of one-tail p-values, no matter how well justification is. 10. Statistical applications in environmental sciences. The following is a list of p-value fallacies, incorrect interpretations. 1. The p-value is the probability of rejecting the null hypothesis. 2. A high p-value proves that the null hypothesis is true. 3. 1p is the probability that the results will hold up when the experiment is repeated. 4. 1p is the probability that the alternative hypothesis is true. 5. The p-value is the probability that the null hypothesis is true. 6. P-value is the probability that the result was due to sampling error. Be noted that all 6 of the above propositions are wrong interpretations of p-values. 8. P-hacking. Remember the coin toss experiment we described in the beginning to test how lucky a person is. 2 ways the person can cheat are by changing the threshold value and increasing the no of trials. Similarly, experimental scientists unethically resort to many practices to decrease the p-value. A low p-value is desirable, as a p-value lesser than the alpha p less than 0.05 would reject the null hypothesis and lead to a conclusion of statistical significance. Some of these tricks include: 1. Try different tests, parametric and non-parametric, and picking the one with lowest p-value the statistical test that will be used. For example, unpaired t-test should be clearly specified as part of the experimental design. It is not fair to try different tests and go with the one that gives lowest p-value. 2. Dynamic sample size and stop when p is lower than threshold. Sample size should clearly be decided as part of the experimental design. It is not fair to change this till p-value is less than the threshold. 3. Slice and dice the dataset to get lowest p. Obviously an unethical practice. We should use all of the elements of our dataset without slicing and dicing. 11. Statistical applications in environmental sciences. 4. Cherry picking the dataset to get lowest p. Obviously an unethical practice. We should use all of the We should use all of the elements of our dataset without picking certain values that affirms our preconceived conclusions. 5. Play with outliers. Remove one or more selectively to get desired p. Obviously an unethical practice. We should use all of the elements of our dataset without removing any outliers manually. In case outliers need to be removed, a formal statistic test such as Grubb's test can be used for this. All of the above are cheating and construes scientific misconduct. As already mentioned, statistical hypothesis testing based on p-values is based upon the threshold significance level, which is nothing but an arbitrary value. Statistical significance is usually denoted by the symbol in graphs. Overemphasizing the statistical significance and asterisk is sometimes referred as stargazing. P-values depend largely on sample size. It is easy to get very low p-values with huge sample size with tiny effect, or tiny sample size with huge effect. P-value answers the question, is there a significant evidence of difference? That question is different from, is there an evidence of significant difference? P-value does not answer that question. Difference between sample means might be tiny, or scientifically negligible, yet decision based on p-value could be statistically significant. Add on to the woes, many studies have revealed that p-values are not very well reproducible. Instead of p-values, the current consensus among the statisticians is to use 95% confidence intervals. 9. P-values and confidence intervals. Confidence intervals and p-values are very well connected. A 95% confidence interval is similar to 0.05 significance level as already explained. The question is, does the range of values defined by 95% confidence interval include our null hypothesis? For example, while comparing the difference in mean between two groups. Null hypothesis is that the group means are same, or the difference between two group means is 0. If 95% confidence intervals of difference between sample means does not include 0 are null hypothesis, then p less than 0.05. Inversely, if it includes 0, then p greater than 0.05 and indicate a statistically significant difference. Let us consider another example. A random sample consisting of 10 individuals volunteered to have their body temperatures measured to know whether they have normal body temperature or not. Mean body temperature was found to be 36.8 degrees Celsius. The width of 95% confidence. 12. Statistical applications in environmental sciences. Interval was found to be 0.3 degrees Celsius and therefore 95%. See about the sample mean ranges from 36.8 minus 0.3 to 36.8 plus 0.3, that is 36.5 degrees Celsius to 37.1 degrees Celsius. Our null hypothesis of having no fever is 37 degrees Celsius. Does our obtained 95% C include the null hypothesis of 37 degrees Celsius? Yes, it does. So, p greater than 0.05 and we can conclude that there is no statistically significant difference from the null hypothesis. 10. FDR and statistical power. Decision. Reject null hypothesis. Decision. Do not reject null hypothesis. Reality. Null hypothesis is true. Type 1 error false positive A. No error B. Reality. Null hypothesis is false. No error C. Type 2 error false negative D. We have already defined A plus B as alpha, level of significance. It is fraction of false positives when null hypothesis is true. A related term is false discovery rate FDR, which is A plus C. FDR is defined as fraction of false positives out of statistically significant results. If the result is statistically significant, what is the probability that null hypothesis is really true? Note that for both level of significance and FDR, numerator remains same, fraction of false positives, but denominator is different. While significance level is based out of all results where null hypothesis is true, i.e., all results that in reality have no effect difference etc., FDR is based out of results with a statistically significant conclusion. FDR depends upon prior probability, the context of experiment akin to Bayesian statistics. FDR and prior probability will be elaborated in the module of Bayesian statistics. Another related term is statistical power, which is C plus D. It is fraction of statistically significant results out of all results where null hypothesis is false. The statistical power is the probability to obtain a statistically significant result assuming a certain effect size in population. Power depends on sample size, variability, choice of alpha and hypothetical effect size. A high power is obtained when 1. Large sample size is used, 2. Looking for a large effect or large difference or a strong correlation etc., and 3. Data with little scatter, small variance and SD. 13. Statistical applications in environmental sciences. 11. Summary. A. Statistical hypothesis is a 4-step sequential process. Significance level should be defined first, then null and alternative hypotheses must be defined. Finally, based on obtained p-value, the fate of 2 hypotheses is decided. It is cheating to change the decided significance level, or changing the sample size and other numerous ways p-values can be hacked. B. Significance level should be chosen based upon tolerance limit to 2 types of errors, type 1. False positives and type 2 false negatives, circa. P-value is defined as, if the null hypothesis is true, what is the probability that random sampling would lead to difference as large as or larger than that observed in this study? It is more essential to know how p-values are correctly interpreted rather than how p-values are calculated. D. A low p-value does not mean differences are scientifically significant, or finding interesting or warrant further funding. P-value answers the question, is there a significant evidence of difference? Not, is there an evidence of significant difference? E. If 95% C does not include null hypothesis, then p-value must be less than 0.05. If the range does include null hypothesis, then p greater than 0.05. This connection is important. 1. 3. Statistical applications in environmental sciences. Module 18, T-distribution and tests of significance based on T-distribution module. 1. Introduction. Students' T-distribution is an important probability distribution in statistics and is used in a number of statistical significance tests, t-tests being the most common and important amongst those. T-tests are used for comparing means of 2 groups. If the objective is to know whether 2 group means differ significantly or not, statistical hypothesis testing, a t-test is not even required. Plotting 95% C of the difference between sample means would suffice. A manual t-test is no more robust or powerful than 95% C of differences for hypothesis testing, but a t-test in computer returns exact p-value that enables us to decide on significance for the evidence of differences if any. This module details the t-distribution, performing 2 kinds of t-tests, paired and unpaired t-tests manually, and most importantly, interpreting the p-values. 2. Learning outcome. A student's t-distribution. B. C of mean difference. C. F test. D. Homoscedasticity. E. Matched t-test. F. Paired t-test. G. Unpaired t-test. 3. T-distribution. T-distribution. Student's T-distribution is a type of continuous probability distribution with exact probabilities of every t-scores known under the assumption of null hypothesis. This enables us to calculate p-value from a given t-score. We have seen how t-distribution is computed in Module 16. First, we calculate t-score t-ratio by dividing difference between sample mean and population mean with standard error of the sample mean. Distribution of these t-ratios plotted as in a probability histogram is called t-distribution. The shape of t-distribution depends only on degree of freedom df. With small df. 4. Statistical applications in environmental sciences. Distribution is fat-tailed platykurtic, while with large values of df, distribution become almost indistinguishable from normal Gaussian distribution with thin tails. For each values of df, t-distribution can be calculated using intricacies of calculus. At each of these distributions at each df, we can calculate the area under the significance level, the threshold p-value, alpha, at either of the tails. These values can be presented in a tabular format, the so-called t-distribution tables, where one can look up a value called t-critical from a combination of df and significance level, for e.g., df equals 15 and significance level equals 0.05. One can compare this t-critical value found from the table and the t-score calculated from the data to make inferences about statistical significance. If t-critical at significance level of 0.05 is less than score, we can infer that p-value must be less than 0.05 and can reject the null hypothesis. T-distribution was developed by W.S. Gossett, who was working at Guinness Brewery in Dublin, Ireland then. To maintain the trade secrets of the brewery, Gossett had to publish the findings anonymously using a pseudonym, student, hence the name of the distribution. Ronald Fisher, the famous population geneticist and the father of statistics, was the first one to refer the distribution as t-distribution. T-distribution is an important probability distribution involved in a number of statistical significance tests. In Module 16 we have seen how this distribution is used while calculating confidence interval of the sample mean. T-distribution is used in calculating confidence intervals of many other statistical measures as well, for example, difference between 2 sample means, as we will shortly learn in this module. T-distribution is also used for t-tests as explained in this module, linear regression analysis and Bayesian analyses, discussed elsewhere in this MOOC. Let's consider the most important test of significance for comparing means of 2 groups, t-test. 4. Unpaired t-test. Unpaired t-test is used to compare means of 2 independent, unpaired or unmatched groups. For example, marks of 2 groups of students, females versus males in a class. Let's consider an example. Data from Franzier et al. 2006 who examined concentrations of neurotransmitter norepinephrine required to get maximal relaxations of urinary bladder muscles of young rats. 5. Statistical applications in environmental sciences. We can all calculate values of mean, standard deviation. Remember, this is a sample, not population, and we should use sample SD equation and standard error of the mean for both of these groups exactly as we have learned in descriptive statistics. Statistics old rats young rats. Let us first define our null hypothesis and alternative hypotheses. H0. Group mean for old equals group mean of young. Difference between two group means is 0. HA. Group mean for old does not equal group mean of young. Difference between two group means is not 0. 6. Statistical applications in environmental sciences. 5. Difference between sample means. Difference between sample means are easy to compute. Here, sample mean of young rats is higher than old rats. The difference between them is 23.55. 6. Confidence interval of the difference between sample means. In Module 16 we have learned how to compute 95% C of sample means. Remember the formula used to calculate the width W of 95% C is W equals Tx SEM, T being a constant from T distribution and SEM being the sample standard error of the mean. To calculate width of 95% C of difference between sample means, a similar formula is used, W equals Tx, standard error of the difference between sample means. Therefore, first we need to calculate standard error of the difference between two means. The following formula is used, where S1 and S2 are sample standard deviations of groups 1 and 2 respectively, and N1 and N2 are sample sizes of group 1 and 2 respectively. Substituting values from rat example in this formula, the standard error of the difference between sample means can be calculated as equals square root 16. The exact value of this standard error of difference between sample means uses a slightly different, albeit a complicated formula that is being omitted here for the sake of brevity. Calculated using that formula, the exact value of the standard error of difference between sample means is 6.67. To calculate the width of 95% C, we have to multiply this standard error with a constant from T distribution T. Remember that T depends only on DF and level of significance. Level of significance is 0.05 for 95% confidence level and the degree of freedom is N1. DF for each group need to be 7. Statistical applications in environmental sciences. Calculated and some of these DF should be used for this calculation. DF for old rats is 9 minus 1 equals 8 and DF for young rats is 8 minus 1 equals 7. Combined DF is 8 plus 7 equals 15. For significance level 0.05 and DF 15, T is 2.1314. Therefore, W is i.e., 23.55. 95% C is mean plus or minus W equals 23.55 14.22 to 23.55 plus 14.22 equals 9.33 to 37.77. Remember that we have learned about null hypothesis in Module 17. While comparing means of two samples, null hypothesis is that there are no differences between sample means, or the difference between mean 1 and mean 2 is 0. We have also learned in Module 17 a crucial connection between 95% C and P in statistical hypothesis testing. The connection is that if 95% C do not include value of null hypothesis, P value should be lesser than 0.05 and we can conclude that the result is statistically significant. In our above example, null hypothesis is that the difference between two sample means is 0. Does the range of 95% C includes this null hypothesis, i.e., 0? As 9.33 to 37.77 do not include 0, we can conclude that p-value must be less than 0.05 and result is statistically significant. Remember that we are deducing this conclusion only from the 95% C, even before performing t-test. If the objective is to compare two sample means to know whether difference is statistically significant, calculating 95% C of those differences would suffice and is robust. Manual t-tests that do not calculate exact p-value and conclude such as p less than 0.05 is completely optional. However, a t-test using computer produces the exact p-value, like 0.0499, which is a lot more informative than conclusions such as p less than 0.05, and therefore preferable over conclusion arrived using 95% C alone. The width of C depends upon following three factors. 1. Variability. Low SD consistent data would lead to narrower C. 2. Sample size. Large N would lead to narrower C. 3. Degree of confidence level. Lower confidence would lead to narrower C. 8. Statistical applications in environmental sciences. 7. Unpaired t-test. Assumptions. Before performing an unpaired t-test, we should make sure that the set of assumptions for this test is not violated in our data. The set of assumptions are 1. Subjects have randomly assigned to one of two groups. 2. Each element, individual measurements or values, are independent of other such elements. 3. Measurement is accurate. 4. Samples came from a normal or nearly Gaussian distribution. 5. Two samples follow homoscedasticity, i.e., they have nearly equal variances or standard deviations. Sample sizes between groups do not have to be equal. First three assumptions: random samples, independent measurement, accurate data, are a familiar set of assumptions used universally in a number of statistical tests. To detect whether our fourth assumption is valid, we should detect whether our samples came from a normally distributed population. A rough approximation for which can be done using visual interpretation of histograms, or by calculating kurtosis and skewness levels and deciding are these values fall within values for approximately Gaussian distribution. For a more formal test, D'Agostino-Pearson Omnibus K2 test can be performed using a statistical package like GraphPad Prism. If the inference is that the populations are significantly deviating from Gaussian distribution, a non-parametric test like Mann-Whitney U-test or Wilcoxon-signed rank test both are not available in Excel. Use statistical package like GraphPad Prism. For testing assumption of homoscedasticity 5 that standard deviations of two groups are nearly equal, an F-test is usually performed. To do F-test, first calculate F ratio. Equals S1 per second 2, where S1 is standard deviation of group 1 and S2 is standard deviation of group 2 for our earlier example of rat bladder. Equals S1 per second 2. Equals 16.09 10.362. Equals 2.41. 9. Statistical applications in environmental sciences. What are the degree of freedom for this ratio? There will be 2 df, one for numerator dfn, and other for denominator dfd, both will be respective group size -1. As seen earlier, dfn equals 8 and dfd equals 7. From these three numbers one can calculate p-value. We can also calculate critical p-value by using F distribution table. Remember that dfd df1 is across and dfn df2 is vertically down. 8 versus 7 3.7257, as in this example, is different from 7 versus 8 3.5005. We should be meticulous not to make such an often made error in this step. As table value critical F, 3.72, is higher than our obtained F ratio, 2.41, we can conclude that P greater than 0.05 and our variances are not significantly different. Whenever looking at T or F or chi-square table, remember that if table value is higher than obtained value, P greater than 0.05, and conclude, N is not significant. If table value is less than test value, P less than 0.05. A more accurate computational method calculates exact p-value of F-test. For our earlier example, P equals 0.2631, which is indeed greater than 0.05. Variances are not significantly different. What if P less than 0.05 with a statistically significant conclusion about variances of two groups? A usual practice is to perform a modified t-test that allows for unequal variances. Such an option is available for 10. Statistical applications in environmental sciences. Excel. However, Moser and Stevens, 1992 concluded that modified t-test that allows for unequal variances should not be used, as the results will be misleading. If F-test returns a low p-value significant, or unequal variances, perhaps the best practice is to ignore the result and go ahead with t-test assuming equal variance. T-test is fairly robust to violations of assumption of equal variances as long as sample sizes are not tiny, and two groups have approximately equal sample size. That means you really don't need to do F-test before a t-test, simply perform normal t-test that assumes equal variances. As explained previously, even t-test is not necessary. 95% C of differences between means would be enough to know whether P less than 0.05. 8. Performing an unmatched t-test. Performing an unmatched t-test is straightforward. First, we have to calculate t-ratio, which is identical to the t-score we calculated while discussing about the derivation of 95% C of the sample mean in Module 16. To calculate t-ratio in t-test, following formula is used. T-ratio equals difference between sample means, standard error of the difference between sample means. Note that for performing t-test all we need to know are mean and standard deviations of two groups that we are comparing. Raw data is not required. If raw data is given, we first have to calculate mean and standard deviations of those two groups. In our rat bladder example, difference between sample means equals 23.55, standard error of the difference between sample means equals 6.67. T-ratio equals 23.55, 6.67. Equals 3.53. As in the case of F-test, next step is to look up t-distribution table for critical t-value given a significance level in df. For 15 df at 0.05 alpha, let us look up the table for t-critical value. 11. Statistical applications in environmental sciences. T-critical is 2.131. As the t-critical from table 2.131 is lower than calculated t-ratio, 3.53 p-value is inferred to be less than 0.05, we reject the null hypothesis and conclude that the difference between sample means is statistically significant. Had our significance level been 0.01, t-critical from the table 2.947 would have been still less than the calculated t-ratio, 3.53, so we can further infer that p-value must be less than 0.01 and differences must be very significant. Actual p-value calculated in a slightly complicated manner by software such as Excel is 0.0030, which is indeed less than 0.01. You can also use a web-based calculator that computes p from t and df. In case calculated t-ratio is negative, no problem, take the absolute value and infer the results. The sign indicate the direction of difference. For example, old rats having larger sample mean than young rats. Had our calculated value been minus 3.53, results would have been still same, p less than 0.05. P-value depends on the following three factors. 1. If mean differences is much greater than 0, i.e., two groups are so much different, p-value will be smaller. 2. If data are very consistent, i.e., low standard deviations, p-value will be smaller. 12. Statistical applications in environmental sciences. 3. If sample size is large, p-value will be smaller. T-ratio can also be calculated by another formula which some students find easier. However, method through SE of differences explained earlier is advantageous, as it enables us to calculate 95% C of the differences. Yet another method utilizes calculating z-score. This method requires us to know exact population mean and population standard deviation beforehand. As already explained, in vast majority of cases except for simulations, the properties of true population, including mean and standard deviation, remain unknown to us. Therefore, practical utility of method through z-score remains negligible with empirical scientific data. 9. Overlapping error bars. Suppose you have plotted mean plus or minus SD in a bar chart with SD shows as error bars extending to both sides of mean. What if you saw two groups SD error bars overlapping? Does it mean the differences between the sample means not significant? As SD captures only the scatter or variability of individual elements, SD overlap tells us nothing in reality. Suppose you have plotted mean plus or minus SEM and the SEM error bars overlap. Only conclusion we can make is that p greater than 0.05. However, if SEM error bars do not overlap, you cannot conclude the reverse, that the difference is significant. It could be significant or it could be not significant. Suppose you have plotted mean plus or minus 95% C and the 95% C error bars overlap. It tells us nothing. Differences could be significant or not. What if 95% C error bars do not overlap? That would. 13. Statistical applications in environmental sciences. Mean p less than 0.05 and difference is statistically significant. Therefore, to know whether difference between two group means is statistically significant or not, the easiest way is to plot mean plus or minus 95% C in bar charts to see to the 95% C error bars overlap. If they do not overlap, a crisp conclusion that p less than 0.05 and difference to be statistically significant can be made without even performing any further tests. If they do not overlap, in that case you can calculate standard error of the differences between sample means, and calculate 95% C and make inferences about p-value. If range includes 0, then p greater than 0.05 and if range do not include 0, p less than 0.05. Type of error bar conclusion if overlap conclusion if no overlap. SD no conclusion SEM p greater than 0.05 no conclusion 95% C no conclusion p less than 0.05. Manual calculation of t-test is no more advantageous than the conclusion arrived from 95% C. However, computational t-tests have advantage. It informs us exact p-value to let us know whether we have significant evidence of difference, not evidence of significant differences. Exact p-value also enables us to spot cases of borderline significance. For example, p equals 0.0499. I would be skeptical to read statements like, differences were found to be significant with p less than 0.05 feet. 10. Paired t-test. In situations where corresponding measurement is made between individual elements of two groups, a matched or paired or independent t-test is done. Examples include before and after analyses, or matched control versus treated. For example, subjects with treatment only on left eye and no treatment on right eye. Another example include each student's individual performance in mid-semester test 1 and mid-semester test 2. Assumptions for paired t-test. 1. Random samples. 14. Statistical applications in environmental sciences. 2. Accurate data. 3. Independent measurements of each pair from other such pairs. 4. Differences between matched values follow roughly Gaussian distribution. Note that individual measurements need not assume to have come from populations that are Gaussian. This assumption is explicitly about the differences between two measurements. Note also that assumption about equal variances that is needed for unpaired t-test is not required in paired t-test. Let us consider an example from Darwin, 1876. He wanted to know whether self-fertilized or cross-fertilized seeds produce taller plants. He planted each pot with self-fertilized seed and cross-fertilized seed. By doing this, Darwin controlled for any changes in temperature, soil, light intensity, etc., as all would be same for the same pot. By 15. Statistical applications in environmental sciences. The above data can effectively be presented as before-after plot with change of each individual measurement is shown. This is created using Excel. Let us first define our null hypothesis and alternative hypotheses. H0, mean difference between paired observations is 0. HA, mean difference between paired observations is not 0. 11. 95% confidence interval of the difference between sample means. First, differences between each pair of values are calculated, third column of earlier figure. These differences are treated as raw data, and mean of these data in SEM are calculated exactly as we would for any other set of data. 95% C is calculated exactly as we would for mean T. SEM. In our example, mean of differences equals 2.62 inches. SEM equals 1.22 inches. 0. 5. 10. 16. Statistical applications in environmental sciences. 12. Paired t-test. For paired t-test, we need to compute t-score, which is very easy to calculate. T-score equals mean differences, SEM, exactly as in unpaired t-test. As calculated in last section, mean differences equals 2.62 inches and SEM equals 1.22 inches. Therefore, t-score equals 2.62, 1.22. 17. Statistical applications in environmental sciences. That the difference between sample means is statistically significant. But you should promptly infer that it is only a borderline significance. Remember that the exact same conclusion we had already been inferred using 95% C in the last section, so t-test is not really required for testing the statistical significance. Had our significance level been 0.02, t-value from table would be 2.624, one value right from our earlier value, which is far higher than the calculated t-ratio, 2.15, so the exact p-value must be greater than 0.02. That would mean our p-value must be somewhere between 0.02 to 0.05. The exact p-value calculated by software, one can use a web-based calculator, is 0.0497, which is indeed less than 0.05 and indeed is pretty borderline. 13. Summary. A. For hypothesis testing involving means of two groups, a 95% C of the difference is in. Sample means would suffice. T-tests are completely optional. B. Standard error of the difference between two sample means is computed using the equation. C. Width of 95% C is standard error xt. D. If 95% C of mean differences do not include zero null hypothesis, then differences can be concluded as statistically significant and p less than 0.05 e. T ratio is ratio between difference between two sample means and standard error of the difference.